Initial and final value theorems. By the end of this section, given a variable in the frequency domain, you should be able to identify if that variable is stable or unstable based on the poles in frequency domain. You will be able to determine the steady state value of our variable in the time domain using the final value theorem, and you will be able to determine the initial value of our variable in the time domain using the initial value theorem. So what do the initial value and final value theorems do? Well, if we have a dependent variable, so a variable that is a function of time, and we put it into the frequency domain by taking its Laplace transform, so it's now in the Laplace frequency domain, or it's a function now of S, we can assess its initial value and its steady state value, that is to say its value after a long time has passed. We can assess those values in the time domain while staying still in the frequency domain. However, before we can apply these rules, this is only going to be valid if the variable is stable, which is to say that in the time domain, given enough time, does the variable go to one constant value. So why is this going to be useful? Well, briefly, if we have our variable in the frequency domain, what we've been doing before is we try to manipulate the right-hand side so that we're going to be able to take the inverse Laplace transform and then figure out what our variable is in the time domain. Well, there's some times where taking the inverse Laplace transform might be very difficult. The algebra, we just might not be able to get it into a form that appears on our Laplace transform table, or maybe we don't want to take the time for one reason or another to go back from the Laplace frequency domain into the time domain. What we can still find out, though, is some properties of the function in the time domain, its initial value and its steady state value, without having to actually return to the time domain. So what does this look like graphically? What are we doing? So here's a commutative diagram similar to what we saw when we were first looking at using our Laplace transform. So this is where we're going to often start, is again we have the ODE in the time domain. And where we want to end up is in the far right if all we really want to know is what is the value of our dependent variable at time is 0 and the value at time, we'll call it infinity, but we call this the steady state value of our dependent variable. We have two paths that we're going to be able to take. So this is kind of an extension of what we were looking at before. If we start out with our ODE, we can use that, take that ODE and apply calculus to it and put in all the information we're going to need, and we can solve it for x of t in general. Then, if we know x of t, we know the value of our dependent variable everywhere. Any value of t, 0 or any positive value of t, we can put into the left-hand side, into the right-hand side, and we can figure out what that value of x is going to be. So we could put in a value at 0 and figure out x of 0, the initial condition, which actually we would need to know anyway to solve this problem. And we could put in a large value of t, and we could figure out what I'm calling x of infinity. So the steady state value of x, what's its value after a long time? And actually, if we take this lower blue path, we can put in any value of t between 0 and a very large value, and we know exactly what x is doing. Now, we saw that this path can be difficult. It might be difficult or time-consuming to do this calculus step to find our x of t, but then once we know that, then it's easy to put in 0 or a large number. Okay, let's take an alternate path, though, presented with the ODE in the time domain, but we still want to get to knowing what is x of 0 and the steady state value of x. So an alternate path we can do is we can take the Laplace transform of both sides, and we can find our ODE now in the Laplace frequency domain. So like before, it turns it into an algebra problem where next step is still going to be basically the same as what we saw before, is let's take that ODE that we took the Laplace transform of and isolate the x of s term. Here again, I'm using x as kind of this generic dependent variable of, well, lowercase x is a function of time, uppercase is a function of frequency, but we can do our algebra and we can isolate x of s here. Now, if, again, all we're interested in is getting to this lower right corner here, we can actually stay completely in the frequency domain, we don't need to do an inverse Laplace transform. What we can do is apply Initial Value Theorem, IVT, Final Value Theorem, FVT, and we can figure out what's happening in the time domain. So again, it's a way of staying in the frequency domain, but knowing some information about the time domain. Now, a drawback of going with this upper path is that Initial Value Theorem and Final Value Theorem, as their names imply, only what's going to tell us what's going on initially and after a long time, the final value or the steady state value. It tells us nothing about what's happening in between. Whereas if we take this lower path, once we know x of t and solve that, we can put in any t and we know exactly what's happening at any time. So we're limited in what we know about the behavior of our variable in the time domain because we only know what happens at the beginning and the end and nothing in between. In Unit 2, we'll get into more about knowing what happens in between. But for now, knowing what happens at the steady state, especially in the time domain, is going to be important for us to know.